Hi everyone, so we'll do lecture 20 today. So this is Math 103, lecture 20. So last time we defined sequences and various properties of sequences, such as what it means for a sequence to be bounded, or what it means for a sequence to be monotonically increasing. We also defined the notion of convergence for a sequence. So let me start by recalling the definition of a sequence. So sequence just means a list of numbers, and we usually denote it in a compact way by writing it in the form a sub n, where n starts at least with 1. This 1 could also be 0. It's up to your convention to determine where your sequence starts. And this just means, this is just a shorthand for the list of numbers a1, a2, a3, a4, and so on. And we say that the sequence converges. We say that sequence a sub n converges to some number L if the terms of the sequence gets arbitrarily close to L. Not just close, but arbitrarily close. That means that you can get as close to L as possible as n gets bigger and bigger. It's bigger and bigger. Okay, so the way we think about this, first of all, the way we write this is we write this as limit n goes to infinity of a sub n equals to L. Now, if there is no such number L, we say that the sequence diverges. So otherwise, we say that the sequence diverges. So this is something we discussed last time, and I gave you some examples. But what I want to do is I actually want to give you a rigorous definition of convergence that mathematicians use, and it's also in the book. And this is to give you a sense of what it really means to converge, what it really means to become arbitrarily close. So the way you should think about this is that you have a sequence, which is a list of numbers, and you're claiming that it converges to some number L, for example. What this means is that no matter how close you want to get to L, so if you specify your threshold of being close to L, let's say you want to be 1/100th away from L, then eventually all the terms in your sequence will be that close to L. So if you specify your threshold to be 1 over a million, so you want to say you want to be as close to the limit L by 1 over a millionth, so basically up to 6 decimal digits, then in fact the terms of the sequence will be that close to L if you go far enough into the sequence. So eventually all the terms will be that close to the limit L. And how do we write this rigorously? So rigorous definition of convergence of a sequence. And so here's how it goes. So we say that the sequence converges to the limiting number L if there's some quantifiers. For every epsilon, which is some number, bigger than 0, so no matter how small, that's the key. So epsilon could be 1 million if you like. Or epsilon could be 1 over a billion. No matter how small, as long as it's positive, no matter how small, we can basically find a number. After that number, all the terms of the sequence are epsilon away from L. So we can find a number n sub epsilon. So this is just some number, some natural number depending on epsilon. Some natural number which depends on epsilon. This is why we write epsilon as the subscript to indicate that this is not just any number, it's a number which depends on epsilon. Such that a sub n, the terms of the sequence, minus L, so this is how far away you're from the limit, is less than epsilon for every n starting at this number capital N sub epsilon. So this just means, this inequality just means that, you're epsilon away, you're in the epsilon neighborhood. So that means the terms a sub n's are they're in the epsilon neighborhood of the limit L. So you really are close to the limit L. Okay. So here's one way to rewrite this inequality. So that's the definition. So let me just maybe say it one more time. So a sequence AN converges to L if for every epsilon bigger than 0, no matter how small, we can find some number, capital N sub epsilon, so it's just some number that depends on epsilon, such that for every n bigger than or equal to capital N sub epsilon, the difference between the terms nth term of the sequence and the limit is less than epsilon. So you're really close to the limit L. So let me rewrite this inequality for maybe further understanding. So suppose so a sub n minus L less than epsilon. Well, what does this mean? Well, what this means is that if you look at the stuff inside the absolute value, a sub n minus L, this is between epsilon and minus epsilon. So this is just a definition of absolute value. If an absolute value of something is less than epsilon, it means that the thing inside the absolute values is less than epsilon and bigger than minus epsilon. Now, we can also rewrite this last inequality by adding L to both sides of this inequality. We get that AN is less than L plus epsilon and is bigger than L minus epsilon. So the second inequality is obtained from the first inequality by adding L to both to all the sides of the inequality. Well, this just means that AN is very close to L. It's between L minus epsilon and L plus epsilon. You should think of epsilon being small. So that's why this makes sense that this could be a definition of convergence, because the terms are getting closer and closer to the limit L. So here is a graphical way to explain this definition. So graphically, here's what it means. So graphically, limit n goes to infinity of an equals to L. In other words, limit to an's converging to L means the following. So if you plot the terms of your sequence as follows. So basically at 1 we're going to plot A1, at 2 we're going to plot A2, 3 we're going to plot A3, and so on. And here is going to be n sub epsilon minus 1, and then onwards n sub epsilon and n sub epsilon plus 1, and so on. So what this means is that here's your limit L. This is the line y equals to L, if you like. So this is a horizontal line, y equals to L. So here's my x-axis, here's my y-axis, and I'm going to plot the points n comma a sub n for each n. Okay? And you also have L minus epsilon and L plus epsilon. These are important lines, so let me draw them. So let's use different colors. Let's say this is L plus epsilon. This is the line L plus epsilon. And let's say this is L minus epsilon. So the definition of convergence of sequences means that once you specify the epsilons, like if you have for any given epsilon, then there will be some number n sub epsilon, which is I've indicated here, such that after this point, after n sub epsilon, all the terms of the sequence will be between these two lines, L minus epsilon and L plus epsilon. In other words, if you plot the sequence, so let's say here's A1. So that's why I'm plotting the point 1 comma A1. So to plot the second point, I have to plot it over 2. I want to plot the point A2. And it could be here, say. This could be A2. And I plot A3, maybe it's here. I plot A4, maybe it's here. A5, maybe it's here. A6, maybe it's here. A7, maybe it's here. A8, maybe it's here. And then n sub epsilon minus 1, maybe it's here. But after, I don't know what happens in the first n minus epsilon minus 1 terms, but after starting at n epsilon and onwards, you must fall between these two lines. You can't escape the blue line and the red line. That's what it means. So the tail of the sequence will be between these two lines, L minus epsilon and L plus epsilon. And that's what this means. This inequality, an minus L being less than epsilon, this should be true for every n starting at n sub epsilon and going onwards. Right. So basically, as you make epsilon smaller, then an minus L being less than epsilon means an is even closer to L. Oops, sorry. Okay, good. So this is just good to keep in mind that notions of convergence actually have precise, rigorous mathematical definitions. So if you look at this example we discussed last time, we discussed this example of -1 to the n as our sequence. So this is a sequence whose nth term is given by -1 to the power of n. So if you write down the terms of the sequence, you get the following. So when n is 1, the first term, you get -1 to the power of 1, which is -1. The second term is -1 to the power of 2, that's 1. The third term is -1 to the power of 3, which is -1. And then 1, and so on. Alternate signs. So we saw that last time this diverges. And you can kind of see this from the picture, right? If you look at what the terms of the sequence is, so you have this line 1, and you have this line -1. And then the terms of the sequence is like this. At odd indices, so this is like n equals to 1, this is n equals to 3, n equals to 5. At odd indices, you have -1. So at 1, you have -1. At 3, you have -1. At 5, you have -1. At 7, you have -1. At even indices, these guys, n equals to 2, n equals to 4, and so on, you have +1, something like this. So we see that we just get ones and -1s alternating. So there is no L for which we can ever get epsilon close if epsilon is small, right? So I'm trying to explain here that if there was a limit, if there was a hypothetical limit, okay, it would be somewhere here. It would be somewhere, I don't know, let's just draw random. Let's say it would be somewhere here. let's say this would be our hypothetical limit. It doesn't actually exist, but let's try to just play this game in our heads. So suppose this is a hypothetical limit. Well, if this was the hypothetical limit, then the terms of the sequence must get close to L. In other words, they should be epsilon away from L eventually for every epsilon. So then we can just pick epsilon to be very small, like 1 over 100. If you pick epsilon to be very small, like 1 over 100, then that means that eventually you must be in this neighborhood. Eventually, your points must be between L minus epsilon and L plus epsilon. So say epsilon is 1 over 100. Eventually, you must fall in between these orange lines, but you don't. You simply do not fall in between these orange lines for any choice of limit L. And for small enough epsilon, let's say 1 over 1,000 or 1 over 100. Because the terms 1 and minus 1, they're too far apart, right? This is minus 1, and this is plus 1, and they're just way too far apart for us to ever fall into a little kind of tube around L. And so that shows that the sequence does not converge. So there is no L at all. There's no L for which an minus L could be less than 1 over 100. This is our epsilon for all sufficiently large n. Okay, so that shows that the sequence diverges. Must diverge. Okay, good. So let's do 2 interesting examples. Okay, so these are a little tricky, but I think understanding these examples will indicate that you really understand what it means for a sequence to converge. So 2 tricky examples. Okay, I say tricky because if you see it for the first time, you might be a bit surprised maybe, but after we work on these 2 examples, hopefully it will be evident and it will no longer be tricky. So here are the 2 examples I want us to consider. So let's consider the sequence defined by a sub n as follows. So I'm not going to give you the formula, but I'm just going to list out the terms. I'm just going to list out the terms of the sequence, okay? And then you will see the pattern. So the first term of the sequence, a sub 1, is going to be 1. Okay, so this is my first term, a sub 1. The second term of the sequence will be 0. So the second term of the sequence is a sub 2. Third term is going to be 1. That's a sub 3. And then you're going to have 0 for the fourth term, 0 to the fifth term, 2 zeros, and then a 1. That's my sixth term. Then I have 3 zeros. Then I have a 1. See, I'm going to increase the number of zeros each time. Then I'm going to have 4 zeros. And then I'm going to have a 1. So hopefully the pattern is clear. So then we're going to have 5 zeros back to back. And then I'm going to have a 1, and so on. Okay, so that's my sequence. Okay, so the question is, does this sequence converge or diverge? So I think I can maybe zoom out a little bit so you can see the whole sequence. Great. Great. So that's my sequence. And the question is, does it converge or diverge? Yeah, so again, just to emphasize, the pattern is that I'm just increasing the number of zeros in between. And the question is whether this sequence converges or not. So at this point, maybe you could pause the video and think about the answer to this question. But I'm not going to reveal the answer just now. I'm going to actually pose a second question. And then I'm going to answer both. So consider this sequence. This is a different sequence defined by Bn. Oops, sorry. Something weird happened. Let me undo. Great. So now consider a sequence. Consider the sequence B sub n. Okay, there's some glitch for some reason. Hopefully it will work now. Okay, so consider a sequence B sub n, and starting at least 1. So now this is going to be very similar to this one, but slightly different. So it's going to be like this. It's going to be 1 for the first term, then 0 for the second term. Then instead of 1 for the third term, it's going to be 1 over 3. Just to indicate that I'm at the third term, it's going to be 1 over 3. Then my fourth term is going to be 0, just like here. My fifth term is going to be 0, just like here. And then my sixth term is not going to be 1, it's going to be 1 over 6. Keep going like this. So it's going to be 3 more zeros. Seventh term is going to be 0. Eighth term of the sequence is going to be 0. Ninth term of the sequence is going to be 0. 10th term of the sequence is not going to be 1 like above. It's going to be 1 over 10. And then I have 4 zeros. So this is the 11th term, 12th term, 13th term, 14th term. And then I'm going to have 1 over 15. Then I'm going to have 5 zeros. 16th term, 17th term is 0, 18th is 0, 19th is 0, 20th term is 0, and then 21st term, in the earlier sequence it was 1, now it's going to be 1 over 21 to indicate that I'm at the 21st index, but the term I'm putting in is 1 over that, and then so on. So the question is, does this Bn converge? Or diverge. Okay. So at this point, I would like you to pause the video and think about the answers to these questions. And yeah, so maybe one more comment. So note that Bn and An are related as follows. So Bn is actually just An divided by n for each n. In other words, to get the nth term of the sequence Bn, so to get the nth term of the second sequence, you just take the nth term of the first sequence and you divide it by n. Because see, if you have zeros, it doesn't matter because 0 divided by n is 0. And if you have 1, if you divide by n, you exactly get the term in the second sequence. So 1 becomes 1/3, 1 here becomes 1 over 6, and 1 here becomes 1 over 10. So you're dividing it by n. And of course, it's zeros. They're both 0, so it still works. Okay, so now let me reveal the answers to these questions. So it turns out, turns out that the first sequence does not converge. The sequence A sub n actually diverges. So that's because no matter how far we go in the sequence, the terms of the sequence will still contain zeros and ones. So this makes it impossible for the sequence to converge to any particular value. This is very, very similar to the example we just discussed, where the terms of the sequence alternate between -1 and 1. Well, here in the first sequence, A sub n, they don't quite alternate between zeros and ones. Somehow zeros appear more frequently, as you can see. But ones, right, they still persist, like they still show up. No matter how far down you go into the sequence, after billionth term, there's going to be some 1 that shows up. And that 1 is going to mess things up because the 0 and the 1, they're too far apart for the sequence to have a limit L. So if you want to get close to an epsilon neighborhood of a limit L, like in this picture of definition of convergence, you're not going to be able to do it because you have zeros and ones. And so if you if you just think about what that means in terms of the definition of limit, you see that it cannot converge to any particular value. Okay. Well, what about the second sequence, b sub n? The b sub n looks very, very similar to a sub n. However, it turns out that the second sequence actually converges, and it converges to 0. So the sequence b sub n, this converges. And in fact, it converges to 0. Okay, so that's because the non-zero terms of the sequence, 1 over 3, 1 over 6, 1 over 10, 1 over 15, 1 over 21, they are themselves also decreasing towards 0. So, right, so the limit is 0 because, right, so the zeros that show up, that's great. They're already 0, and they're really frequent. And there are non-zero terms, but eventually they get smaller and smaller. After like billionth term, if you see something here that's not 0, it's going to be 1 over a really large number, and therefore it will converge towards 0 in the limit. Okay, so that's that. So let me just recall a definition of bounded from last time. So recall that the sequence an is bounded. An is said to be bounded if there exists some real number m, there is a real number m such that a sub n is at most m for each n. Okay. Now, this just means that basically graphically, it just means that if you were to draw the graph, if you were to plot the sequence points, they would be in between the lines m and the line minus m. Right? That's because this is the same thing as saying an is between m and minus m. So if you start plotting your points of your sequence, so 1, 2, 3, 4, 5, 6. So you plot the point above 1, you plot a1, so maybe a1 is here. You get this point, and then you plot a2, maybe a2 is here. So you plot it over 2, and so on. So no matter how you plot these points, they can't escape. They can't escape between these two numbers, m and minus m. And so that's why it's called bounded. And we usually say in this case that an is bounded by m. Okay. Now, here's a fact that I claimed last time, but I didn't prove. So I'll prove it this time. So here's a fact. If a sequence converges, then it must be bounded. That's the fact. If a given sequence converges, then it must be necessarily bounded. Okay, so let me maybe show the picture, show the proof graphically. It's like this. Okay, so you have your sequence. We know it converges, right? So say it converges to L. So say the limit, let me not write it here, I'll write it underneath. So let's say the limit, let's say that the limit n goes to infinity of a sub n is L. So we know it converges, so let's say it converges to L. Well then, remember this means that you will get into the epsilon neighborhood of L eventually for any epsilon. So let me just pick epsilon to be 1. So that what that means is that, so I have my limiting line L. So I know that the terms of the sequence get close to L. And then I have my threshold. So I'm going to pick epsilon to be 1. So my threshold is going to be L. It's going to be L plus 1 here and L minus 1. Okay, so this just means that eventually the terms of the sequence will fall into between the lines L minus 1 and L plus 1. So the terms of the sequence will eventually lie in between these two orange lines because it converges to L. So let's plot the points of the sequence with blue. So eventually, after point N, I'm just gonna have my sequence clustered in between these lines. Okay, so that's just from the definition of convergence. So AN minus L is going to be less than 1. You're going to be 1 away from the limit for each n starting at some number n. Okay, and all right, that's pretty good because we sort of almost bounded our numbers. We kind of bounded our numbers, but there's also terms before n, right? There are terms that correspond to 1, 2, 3, dot, 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 up to n minus 1. What if they're really big? Well, that's not a problem because there's only finitely many numbers that could be lurking around here. So, okay, so maybe there's some numbers here, maybe a sub 2 is here, maybe a sub 3 is here, maybe a sub 4 is here, maybe a sub n minus 1 is, I don't know, here, right above this sentence. They could be big, that's fine, but there's only finitely many of them. So they're still bounded. So I can still draw a line that makes them in between m and minus m. So, okay, so this is a bit extreme because I don't want to mess. So I'm just going to erase this. So let's say a n sub n minus 1 is somewhere here. Now I can still find m and minus m that bounds these numbers, right? So let me draw that, I don't know, in green. So I can still draw a line m here and a line like minus m here where all the blue dots are in between. So it's still bounded. So the only reason I erased the number here is because then I would have to draw m here and the graph gets messy. Okay, so the point is that if the tail of the sequence is already sort of squished between these lines, then for the first n minus 1 terms, you can just take the maximum of the terms, then you can still bound the sequence, and therefore the sequence is bounded. So more precisely, just define, I guess, the number m to be max of the numbers a1, a2, dot, 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 a sub n minus 1, and then after this, we know that the sequence falls in between L minus 1 and L plus 1, so the absolute value is at most L. Let's just, we can do like L plus 1. Actually, to be on the safe side, let's do absolute value of L plus 1. In case L is negative. So this m should do the job. So this m should do the job. In other words, we get that absolute value of an is indeed m for each n bigger than or equal to 1, right? Because for the first n minus 1 terms, I have already included them in the max. And for the terms that come afterwards, I have this L plus 1 that bounds them. Sorry, and you can see that from the graph. Okay, so for those of you who don't know what max of something means, it just means take the maximum of the quantities that you see inside. So there's only finitely many numbers that I see here, and there's one more number I see here. Okay, just take the biggest one, and that biggest one will bound all of them. And I mean, it's kind of, I think it's more intuitive just from the picture that if the tail of the sequence is squished and the first n-1 terms is wherever they can be, doesn't matter, there's only finitely many of them, so I just can find something even bigger than all of them and make sure all the blue dots, all the dots of the sequence are in fact between n-m and m, and that proves, in fact, that proves the claim that convergent sequence must be bounded, okay? So as a consequence of that, so let me just rewrite again, so thus we proved that convergent sequence is bounded. Now, as a direct consequence, we get that, so as a result of this, we get that if the sequence is unbounded, then it must diverge. If the sequence is not bounded, then it cannot converge. Then it must diverge. Right? Because if the sequence was not bounded, and if it were to converge, then, well, according to the previous fact, it must be bounded, and that's a contradiction. So if the sequence is not bounded, then it cannot converge. So one implication is true. If you have something convergent, then it must be bounded. But of course, the other implication is not true, that if you have something bounded, it doesn't necessarily mean it converges. And in fact, we saw an example earlier. So warning, a sequence could be bounded, but may still not converge. May be bounded, but still may diverge. So for example, -1 to the n, as we saw this example earlier. So this sequence oscillates between -1 and 1. Well, it's clear that this sequence is bounded. It's bounded by m equals to 1. In fact, all the terms have absolute value 1. But it diverges. But it diverges. In other words, if you have a sequence that's bounded, you don't have enough information to just conclude right away that the sequence converges. You need to know more. But if the sequence is unbounded, then we know automatically that it must diverge. Unbounded means like terms are not controlled by any m. The terms just get bigger and bigger or smaller and smaller. They go towards infinity or minus infinity or whatever. So in that case, we can automatically conclude that the sequence must be divergent. Okay, so right. So later on, I will I will prove another fact, that if the sequence is bounded and it's monotone, then it must converge. Later in the lecture, I'll prove that. So monotone just means monotonically increasing or decreasing. So, boundedness and convergence are kind of closed notions, but not exactly the same. So, but before I do that, let me talk about squeeze theorem. Very important. Okay, so squeeze theorem. So what it says is the following. It says that suppose we have 3 sequences. Suppose we have 3 different sequences, AN, BN, and CN. So the first one is indexed by A sub n, the second sequence is B sub n, and the third sequence is C sub n, such that the terms of the sequence can be compared to each other in the following way. A sub n is less than or equal to B sub n, less than or equal to C sub n for each n. And furthermore, let's suppose that, assume that the limit of ANs and CNs converge. So limit n goes to infinity of AN is L. So ANs converge to L, and let's assume that CNs converge to L. So the smaller sequence converges to some number L, and the bigger sequence also converges to some number L. Then the conclusion is that then the sequence Bn also must converge. Okay? And in fact, it converges to L also. In fact, the limit as n goes to infinity of Bn is also L. Okay? So this is kind of geometrically, we're going to see the picture of this. It's not so hard to believe, because you have three sequences. And let me plot the big sequence Cn by red. So we have some sequence. And then, so this is my sequence C sub n. And then A sub n, let me do it with blue. So they all converge to L. So there's this line L. And so they all converge, the values converge to L. Both Cn and An, these sequences, they converge to L, while B sub n, the middle sequence, is between these two terms, right? So no matter how you try to plot the points of B sub n, well, they can't really escape these two lines. So maybe they can try to oscillate or do whatever, but they're always squeezed. As you see, they're always, so they're always squeezed. So maybe the picture is not very clear, but what I'm saying is that they're always squeezed in between these two lines. And so in fact, they're also forced to converge, and in fact, they're forced to converge to the number L. Okay. So basically, like, you can also just prove squeeze theorem just analytically, like using symbols, right? So we know that like AN is less than or equal to BN is less than or equal to CN, right? So just like take the limit of both sides. So naively, let's take the limit of both sides. Okay, this is just supposed to illustrate why you should believe squeeze theorem. Okay, well, I know this is L, and I know this is also L. So then my limit of Bn's is squeezed between L and L. Okay, but what's the only number? What's the only number that's bigger than or equal to L and smaller than or equal to L? Well, there's only one such number. It's L. So we conclude that the limit of the Bn's is also L. Okay, good. So now let's apply squeeze theorem and see why it's actually useful. Okay, so here's applications of two squeeze theorems. So I'm going to give two applications. Applications of the All right, so here's the first application. So example 1. So the question is determine whether this sequence cosine 7n over n, determine whether this converges or not. Converges or diverges, that's the question. Okay, so here's the solution. So basically, cosine 7n, I mean, that's kind of a complicated thing to deal with. Like, I don't know what cosine of 7 times 3 is. Cosine 21, who knows what that is. But we do know that cosine is between -1 and 1. Cosine of anything is between 1 and -1. So in particular, cosine of 7n is also between -1 and 1. This is true for every n. So for each n starting at 1. And so as a consequence of this, we get that cosine of 7n over n, which is the thing that we're interested in, is between 1 over n and -1 over n. Right? So cosine 7n over n is at most 1 over n, because I can just replace cosine 7n with 1 using this part of the inequality. And using the other part of the inequality, I can get a lower bound by replacing cosine 7n with -1. Okay, but let's look at the tail ends, right? So if you want to apply squeeze theorem, in the application of the squeeze theorem, in the application of the squeeze theorem, then this would be like my I'm still trying to get used to this online teaching, so sorry about that. Okay, so this is my AN, and this is my, I guess, CN, and then this thing I'm interested in really is my BN, the thing in the middle. But let's look at the smaller one, right? So limit of n goes to infinity of a sub n. This is just limit n goes to infinity of -1 over n, and that's just 0, because as n gets closer and closer to infinity, -1 over n gets closer and closer to 0. Okay, similarly, limit as n goes to infinity of c of n is just limit as n goes to infinity of 1 over n, which is also 0. So we just showed that the left end and the right end, so the lower sequence and the top sequence, they both goes to 0. So by squeeze theorem, so using this, you apply squeeze theorem to conclude that the limit of the bn's, the one in the middle, is also 0. So limit as n goes to infinity of cosine 7n over n, that's my bn, this is my b sub n, that should also be 0. So in particular, it converges. Okay? Great. Let's do another example, example 2. So let's consider the sequence. B sub n defined by n factorial over n to the n for each n starting at 1 and onwards. So the question is, does this sequence Bn converge? Does it converge or does it diverge? Okay, so for those of you who may not be familiar with this notation of factorial, so recall that n factorial, written n exclamation mark, is just a product of the numbers starting from 1 all the way until n. So this is just a product of numbers, whole numbers, or natural numbers, starting from 1, ending at n. So for example, 4 factorial would be 1 times 2 times 3 times 4, and you can check 6 times 4, it's 24. Okay. So factorials grows rather quickly, right? Because you're multiplying numbers from 1 to n. But n to the n is also very, very large, right? Because it's multiplying n with itself n times. And so we want to understand sort of, does the sequence converge? The ratio Does it converge to anywhere? In some sense, we're really asking about, how fast is n factorial grows compared to n to the power of n. And here's the solution. So we will show that the sequence converge. In fact, we'll show. So we'll show that converges to 0. So solution. So we will use squeeze theorem to show that the sequence n factorial over n to the n, the sequence whose nth term is given by this expression, will show that the sequence whose nth term is given by this expression converges. And in fact, we'll show that the limit n goes to infinity of n factorial over n to the n is actually 0. So what this means is that n to the n grows so much more quickly, compared to n factorial, right? That's why the limit of the ratios is 0. Like, what does it mean, the limit of the ratios is 0? It means that this particular ratio gets smaller and smaller and smaller. In fact, it goes to 0. So that means the denominator is so much bigger compared to the denominator is so much bigger compared to the numerator. That's what it means. Great. So now, how do we apply squeeze theorem? Well, we observe that, well, the thing we're interested in is in n factorial over n to the n. And, well, we know definitely it's at least 0. What about an upper bound? Well, we write down the definition of n factorial, which is 1 times 2 times 3 times all the way until n. And then we divide by n factorial, which is multiplying n with itself n times. So this product is happening n times. That's what it means, n to the power of n. Well, let's split up this fraction by pairing up terms one by one. So I have 1 over n, and then I have 2 over n, and then I have 3 over n, and so on. Then I have at some point n minus 1 over n. That's the penultimate term, and then the last one is n over n. Okay? But now notice that each of these terms is at most 1. Right? So this is at most 1, 2 over n is at most 1, and 3 over n is at most 1, and n minus 1 over n is also at most 1. Well, n over n is actually exactly 1. So in particular, it's also at most 1. That means that this entire expression right here that I'm circling right now, this entire expression is less than or equal to 1 over n. Because it is 1 over n times a bunch of numbers, all of them are at most 1. If you multiply 1 over n by a bunch of numbers, all of which is at most 1, then you're certainly at most, the total thing is at most 1 over n. Okay, so what we have shown is that n factorial over n to the n is between 0 and 1 over n. But now we can apply squeeze theorem, because 0 definitely has limit 0, and 1 over n also has limit 0 as n goes to infinity. So the thing in the middle, by squeeze theorem, must also have limit 0. And I made a typo, I'm sorry. The thing in the middle is not n factorial over n factorial. It's n factorial to the power of n to the n. Right, so this is what we have shown. This is what we have shown. And I'm saying that, let's observe that limit n goes to infinity of 0, this thing is obviously 0, and limit n goes to infinity of 1 over n is also 0. So apply squeeze theorem. We get that the limit of the middle thing, n factorial over n to the n, must also be 0. And that's exactly what I had claimed earlier. Okay, great. So now let me talk about another version of squeeze theorem that might be useful in some applications. And here's what it is. So here's what it is. So suppose we know we have two sequences, and we know that one is less than or equal to the other. So I just have two sequences in this case instead of three. So I just know that an is at most b sub n for n at least one, say. And so because we also know that the smaller one, the smaller sequence, diverges to infinity. So in other words, limit as a limit of the ANs is plus infinity. So diverge, this means diverges. But not just diverges, but it diverges in particular towards infinity. Right? Because you could diverge for many reasons. Like we've seen examples of divergence where terms oscillate between 1 and -1. So that's one way of diverging. Another way of diverging is kind of going towards infinity. Terms are getting bigger and bigger and bigger arbitrarily, and they tend towards infinity. So diverges to infinity, plus infinity. And then the conclusion is that the limit of the BNs also diverge to infinity. Okay, so this is kind of evident, right? Because Bn is bigger than An. So if Ans already get so large to diverge to infinity, then Bns must also do the same, because Bns are even larger than Ans. So indeed, so this is just a parenthetical remark that explains how you should think about it. So because Bns are already bigger than Ans. So this is very similar to comparison tests that we learned when we talked about integrals. And then, so similarly, suppose we have Bn is less than or equal to Cn for each n, and we know that the limit of the Cn's diverge to negative infinity, then we can conclude sorry, this is kind of hard to read. Let me write the word conclude again. So we can conclude that the limit of the Bn's is also minus infinity. And that's because Bn's are even smaller than Cn's. So if Cn's are getting very, very small, namely they're getting very, very negative, so that the limit of the Cn's is minus infinity. So Cn's diverge towards minus infinity. Well, Bn's are even more negative, right? Because they're smaller than Cn. That means Bn's should also diverge towards negative infinity. So because Bn's are even smaller than Cn's, meaning they're more negative, meaning that eventually, so they're even more negative, so it's even easier for them to diverge towards minus infinity. Okay, excellent. So here's so the next thing I want to, well, actually, before I move on to the next topic, maybe I should show an example of this new version of the squeeze theorem, the extended version of the squeeze theorem I just discussed. So I just discussed these results, which I called another version of the squeeze theorem, and I want to show you an application of this particular result. Okay, so what would be an application? So let Bn be n square plus cosine of e to the n. Okay, so cosine of e to the n. So e to the n is the input of the cosine. And let's try to understand the convergence of the sequence Bn. Okay, so as given, it's kind of hard, right? Because we don't know what cosine e to the n is. So anyways, the goal for us is to understand convergence or divergence of the sequence Bn. The convergence / divergence of the sequence Bn, and I'm just saying that at the first sight, it seems kind of complicated. But again, we can use the fact that cosine of anything, in particular cosine of e to the n, is between -1 and 1. No matter what you put inside cosine, what comes out is always between -1 and 1. And so as a consequence of this, and so what we get is that this n squared plus cosine e to the n, which is our Bn, this is by definition the sequence whose nth term is Bn. So we know that this is at least n squared minus 1. So just using this part of the, so I'm just using this part of the inequality to get this one. So now let me call this an, new sequence. Well, now we see that the ANs certainly diverge. So limit of the ANs is just limit of n squared minus 1. Well, as n gets larger and larger, n squared minus 1 gets larger and larger. And so in fact, this diverges towards positive infinity. But Bn's are even larger than an. So limit of the Bn's must also diverge to infinity. So this thing, n squared plus cosine e to the n, the limit of that is also plus infinity. Okay, it's simply because it's bigger than something that already diverges to infinity, so it itself must diverge to infinity. Okay, so next I want to give you an example of finding limits of sequences, and it's a very special example, but it appears as one of the homework problems. I think we're work problem 3, and very similar to that. And here we're going to use L'Hopital's rule in finding the limit. So consider the sequence Bn defined by, so consider the sequence Bn defined by Bn equals to n to the power of 4 over n. Okay? And I want to understand basically the convergence or divergence of the sequence. So in other words, so in case we have forgotten what this means, so we're looking at the sequence, the terms of our sequence is as follows, right? So this means that the first term of the sequence is when you substitute n equals to 1 into the formula. So 1 to the power of 4 divided by 1. That's the first term. The second term is 2 to the power of 4 divided by 2. The third term is 3 to the power of 4 divided by 3. And fourth term is 4 divided by 4. And fifth term is 5 to the power of 4 divided by 5, and so on. So I want to understand where does these terms converge or diverge. So as written, it's kind of complicated, you see, because, I mean, who knows? There's this n that's increasing here, and the exponent is decreasing here, right? And so it's a question of how fast they balance each other out. So a really cool trick to solve this problem is to consider a new sequence. Consider a new sequence which I'm going to call Cn, defined by taking ln of bn's. Okay, so defined by Cn is just ln of bn's. That just means it's ln of n to the power of 4 divided by n. So why is this useful? Well, this is useful because we can use properties of ln. So we can use the property that there's a property of ln that says if you take ln of anything, like literally anything, x, with some exponent inside, so x to the power of k, then you can actually move this k outside. So this k can be moved outside. So this expression is equal to k ln x. So having this identity is helpful because it tells us that Cn is, well, it's ln of n to the power of 4 over n. So I can just take my exponent, 4 over n, and move it outside. And that will simplify the expression because I'm going to get 4 over n times ln n. In other words, it's 4 ln n divided by n. Okay. So this Cn, so the Cn's are just 4 ln of n over n, and somehow this is, to me, this looks simpler than the expression bn. So the goal will be to find the limit of the Cn's first, and then go back and infer information about the limit of the bn's. So how do we find the limit of the Cn's? Here is the L'Hopital's rule going to be helpful. So note that Cn is of the form f of n for the function f of x equals to 4 ln x over x, right? So the sequence values are actually given by inputting a natural number n into this function 4 ln x over x. So if you want to compute the limit of the Cn's, which means computing the limit as n goes to infinity of the Cn's, well, that's the same thing as computing the limit as n goes to infinity of 4 ln over n divided by n by definition of Cn. But then that's the same thing as just computing, instead of working with the natural numbers, let's just compute the limit of the function. So 4 ln x over x. But if you just think about what this means is I'm letting x goes to infinity, and so the top is going to be infinity over infinity, because both ln x diverges towards infinity and x diverges towards infinity as x goes to infinity. So you have this in the situation infinity over infinity, which is an indeterminate form. So we should apply L'Hopital's rule. So the key here was that we, instead of working with the numbers, so here n is like the natural numbers, I can just pass and work with the functions, and so my input x is no longer a number n, but it's a real number x. Right? So x is a real number, n is a natural number. But in terms of the limits, if there is a convergence to be found, it doesn't matter which way you compute the limit. Okay, now if you use L'Hopital's rule, this is going to be L'Hopital's rule. This means that in order to compute the limit, I can just take the derivative of the top and derivative of the bottom. So I can take the derivative of the top divided by derivative of the bottom. Well, the derivative of ln x is 4 ln x is just 4 over x, and derivative of x is just 1. So I just get limit as x goes to infinity of 4 over x, which is 0. That's great. We just computed the limit of Cn, and that was 0. So what do we conclude? So we conclude that the limit n goes to infinity of Cn is 0. That's great. So the sequence C1, C2, C3, ... converges to 0. Okay, so here's the trick. Remember, we wanted to compute the limit of the sequence Bn, which was n to the power of 4 over n. But what we ended up computing is the limit of the sequence ln of n to the power of 4 over n. We showed that this sequence converges to 0. So, but I want to get back to n to the power of 4 over n. So we got to Cn by taking the ln. So if you want to go back to b to the n, b sub n, sorry, you need to exponentiate. So if C1, C2, C3, so on, converges to 0, then consider e to the power of C1 and e to the power of C2 and e to the power of C3. These guys will converge to e to the power of 0, and that's 1. That's the key, okay? Okay, but what is e to the power of Cn? So, but e to the power of C sub n, by definition, is e to the power of ln of 4 over, it's Cn, but what is Cn? Yeah, so Cn was ln of n to the power of 4 over n, but, you know, e to the ln of anything is itself, so e to the ln of a is a, so you just get n to the power of 4 over n here, and by definition, that's bn. So that means that bn's converge to 1, right? So since we have shown that limit as n goes to infinity of e to the Cn is 1, we deduce that limit as n goes to infinity of bn, well, they're the same thing. Bn is equal to e to the Cn is also 1. And so that's the answer to our question. So this is the answer to our question, final answer. In other words, the limit of n to the power of 4 over n is in fact just 1. Okay. Great. So let me go back to one of the things we were discussing earlier, which was about convergence and boundedness. And recall we showed that convergent sequences must be bounded. And we also explained, or gave a remark, that if the sequence is bounded, then it's not necessarily convergent, because we gave an example. We gave a counterexample. So let me just go back to that slide. So let me just go back to the slide. So we were discussing boundedness. And so it was before squeeze theorem. Okay, so here's what we talked about earlier, right? We showed that if you have a convergent sequence, then it must be bounded. However, I gave a warning. A sequence may be bounded, but still may diverge. Namely, this example. But now I'm going to explain a fact. I'm not going to prove it, but it's going to be intuitive, that if the sequence is bounded plus it's monotonically increasing, then it must converge. So if you add one more condition on top of being bounded, such as being monotone, then it must, in fact, converge. So let me scroll back to our blank page. Okay, so the important fact. Important fact. Important fact. Okay, so if you have a sequence, if an is a sequence, is bounded, and monotonically increasing, then in this particular case, in this special case, then we can in fact deduce that the sequence converges. Okay, so again, remark is that we really need both of these conditions. Like we really need, I mean, what I mean is, under these two conditions, we can assume sequence converges. But like if you don't have one of them, it's not necessary that it converges. Of course, it could still converge for other reasons. I'm not saying that if you don't have either of these conditions, you must necessarily diverge. I'm not saying that. I'm saying if you have boundedness and monotonically increasing, then you must converge. Now, of course, you could converge for other reasons. But, well, you have to be bounded, as we explained. But you don't have to be monotonically increasing for you to converge. We've seen examples of various complicated sequences that converges, and they're not necessarily increasing, right? So, but I do want to make a remark that you kind of need both conditions, right? So remark is that you need both conditions. Like if you have negative 1 to the n, this sequence, negative 1, 1, negative 1, 1. So this one is bounded, but not monotonically increasing, but not monotone. And as we see, it diverges. And another example is just the sequence n, whose nth term is n. So this is the sequence 1, 2, 3, 4, dot, dot, dot. So this sequence, this is the second example. So this is certainly increasing. So certainly monotonically increasing because the terms are getting bigger one by one. This is monotonically increasing, but not bounded. And it diverges. But somehow, if you have both bounded and monotonically increasing, you must converge. Right. So again, let me just say one more remark. So boundedness is definitely necessary for you to converge. If you don't have anything bounded, you can't converge. But it doesn't need to be monotonically increasing for you to converge, right? So you could have other examples like negative 1 to the n over n. So if you look at this example, this is like, this example is negative 1 over 1, 1 over 2, you have negative 1 over 3, you have 1 over 4, negative 1 over 5, and so on. This sequence is bounded, certainly, so it's bounded by m equals to 1. All the elements of the sequence has absolute value at most 1, but not monotonically increasing or decreasing. So it's not monotone. Neither increasing nor decreasing because it's just kind of like jumps up and down, right? First it's negative, then it's positive, then it's negative, then it's positive, then it's negative, then it's positive, but it still converges. It still converges. In fact, it converges to the number 0. It's clear that the terms are getting closer and closer to 0 from the negative and the positive side. So good to keep all these examples in mind. But actually, let's apply this fact that I mentioned. Well, we have this fact, important fact. If you have something bounded and monotonically increasing, then it must automatically converge. So here's an example. So, question, does the sequence 2 does the sequence 2, 2.1, 2.11, 2.111, 2.1111, 2.11111, and so on. Does this sequence converge? Okay, so the answer, so maybe you should pause the video and try to figure out the answer to this question. And so the answer is yes. This sequence is bounded. So absolute values are bounded by some number. So let's say, by m equals to 3. Certainly all the numbers are less than 3. And it's monotonically increasing. Right, so because terms are getting bigger and bigger, and so it must. So it converges by the what I call the important fact. Important fact above. Okay. So similarly, if you know that an is the sequence is bounded, and you know, and it is monotonically decreasing, then it must converge. Okay, so that's that. So next, I want to discuss a little bit of the notion of iterating functions or iterating maps. So the word map is sometimes used in mathematics to describe functions. So this next topic is about iterated maps. So we discussed this a little bit last lecture, in lecture 19, which was that one way to construct sequences, it's by iterating a function. It's by iterating a function. So in other words, so suppose f of x is a function. And we have some initial value. So let's say a sub 0 is some initial value that we sort of feed into the function. And then we can define the sequence recursively like this. So then define a sub n to be just by substituting into f the previous term. And this should be for each n starting at 1. So the sequence is like this. So a sub n, so in this case I'm going to start at 0 instead of 1. So well, my first term is just a sub 0, right? So the first term is just a sub 0. Well, the second term should be a sub 1. But a sub 1, but according to this formula, it's f of a0. So a1 is just f of a0. Well, a2 would be, according to this formula, a of 2 should be f of a of 2 minus 1. So f of a1. But f of a1 is same as f of, instead of a1, I write f of a0. So I just keep a0 and I iterate the function f. So similarly, this would be a3 because it's the n equals to 3 term. This would be f of a2, so it's f of a1, so it's 3 times f of a0, and so on. So that's the sequence we get. So the fundamental question is, how do we determine if the sequence converges? That's sort of the fundamental question. How do we determine if this sequence above converges or not? So, well, so say it converged, okay? So let's explain, if it were to converge to some number, let's explain how to find that number, how to find that limit. So this is our thought process, okay? So, so suppose, for the moment, it converged, right? So it converged. That is, suppose that limit of the ANs is some number. So suppose that the limit of the ANs is some number L. Okay. So how can we get information about this number? Well, here's the trick. Here's the trick. So we have the relation A sub n equals to f of A sub n minus 1. So this is in fact how we constructed the terms of the sequence. We kept applying the function f. So to get the next term, you apply f to the previous term. But yeah, by the way, this is another way to think about why we're getting this nested functions, right? Because each time you want to get the next term, you just apply f to the previous term. So I start with a0. Well, to get the next term, I apply f to the previous term. So I get f of a0. To get the next term, I apply f to the previous term. That's why I get f of a0. And then I apply, to get this term, I apply f to the previous term. That's why I keep getting f of a0, and so on. Okay, so that's sort of the key. Now, how do I combine this information about the limit of the ANs and this recursive relation? Well, I can take limit of both sides. So I just take the limit of both sides. So I take the limit n goes to infinity of f of a minus 1. Okay, but now here we need to interchange the limit and the function. There's a function that's kind of obstructing this limit. But if the function is continuous, so assume for now the function f is continuous, and which will be the case in this course, so assume f is continuous, then we can actually interchange the limit and the function. Then we're allowed to interchange the function and the limit. Okay, so what this means is that we get limit n goes to infinity of an equals to limit, this is what we had, n goes to infinity of f of an minus 1. So now I am going to interchange. Limit as n goes to infinity of, instead of writing the limit, I'm going to put f outside. So it's going to be f of, and then I'm going to write down the limit as n goes to infinity of an minus 1. Okay? So what we have shown is that the limit n goes to infinity of a sub n is equal to f of limit as n goes to infinity of a sub n minus 1. Okay, but what is limit of ANs? By definition, I'm assuming it's L. And also, limit of AN minus 1s, it's also L, right? Because, n is going to infinity. It doesn't matter that this is a sub n minus 1 or a sub n or a sub n plus 1. It doesn't really matter. As n gets bigger and bigger, the terms of the sequence a of n minus 1 is going to be L. Like this sequence is the same as this sequence, except shifted by 1, but you're taking the limit as n goes to infinity, so it doesn't matter. So there we go. So we got some interesting relation. We got that L is equal to f of L. So another way, so f of L, same thing, is equal to L. This means that L, this is called a fixed point of the function. So L is a fixed point. Of the function f. So fixed point just means it's an input of the function for which if you apply the function, you get back to the input itself. So f of L equals to L means L is a fixed point of the function. So this is also known as equilibrium point. Now, so similar to what we discussed in chapter 9 about stability of steady states, we also have a notion of stability for iterating maps. So in this case, we have a fixed point of the function. We say that it's stable. We say that L is stable fixed point. In this case, if the derivative of the function. If the derivative of the function, which in absolute values, is less than 1 and is unstable if unstable fixed point if otherwise. So if absolute value of the derivative at L is bigger than 1. So so let me just give an example. So I think this appears, a similar problem to this appears in the word work as well. So hopefully this will help you, the homework. So find the fixed points of the iterated sequence below. So a sub n plus 1 is 1 over 12 times a sub n plus 12 divided by a sub n. And also, once you find the fixed points, classify them as stable and unstable. Okay, so solution. So notice that if you look at the sequence, right, this sequence is given by, so note, a sub m plus 1 is just given by applying the function f to an, where our function, where f of x, is given by 1 over 12 times x plus 12 over x. Okay, so to find the fixed points, so to find the fixed points, we must solve for f of x equals to x. Okay, so this means that we have to solve the equation 1 over 12 times x plus 12 over x equals to x. So then we have x plus 12 over x equals to 12x, which gives us, if you multiply both sides by x, you get x squared plus 12 equals to 12x squared. And then if you rearrange this, you get 11x squared equals to 12. And so you get x squared equals to 12 over 11. And then you have to solve for x, which means you have to take the square root of both sides. But if you take the square root of both sides, you get two solutions, right? You get plus minus square root of 12 over 11. And so there are two fixed points. There are two fixed points. Namely, plus square root of 12 over 11 and minus square root of 12 over 11. Okay, so we found our fixed points, and next we need to classify them according to stable and unstable. So we compute the derivative. So derivative of the function is 1 over 12 times, so what was the function? So it was x plus 12 over x. So derivative is 1 over 12, the constant in front, times derivative of x, which is 1. And then derivative of 12 divided by x, well, you have to write this as 12 times x to the power of minus 1, and then apply the power rule. What you end up getting is that this is minus 12 divided by x squared. Okay, and so now let's look at this, how big the derivative is at the stable, at the fixed points. Now we need to compute f prime of the fixed points. So square root of 12 over 11, that's one of them, and also the one with the negative sign, minus 12 over 11. Okay, so what do we get? So f prime of square root of 12 over 11 is substituting square root of 12 over 11 into the formula for f prime, so into this formula. So we get 1 over 12 times 1 minus 12 divided by x squared. So I just take my input, 12 over 11, under the square root, I square it. Okay, so I get 1 over 12 times 1 minus 12 divided by, if I square the square root goes away, so I get 12 over 11. So then that gives me 1 over 12 times 1 minus 12 divided by 12 over 11 is just 11. And so that's minus 10 over 12, which is minus 5 over 6. And so, actually, similarly, if you do the same computation, similarly, if you do f prime of negative 12 over 11, you get the same answer, right? You get the same answer because if you plug this into here, the negative sign will cancel because I'm squaring it. I see an x squared here, right? If I plug in a negative 12 over 11 square root, if I square it, the negative goes away anyway, so you end up getting the same answer. So I still get minus 5 over 6. So the conclusion is that both the values of the fixed points for the derivative, both of them have absolute value less than 1. So square root of 12 over 11. And so we conclude that both 12 over 11 square root and minus square root 12 over 11 are stable. So what stable means basically is that they will converge through the solution, like the limit of the sequence will converge. And if you look at the textbook, there's more information about iterating maps. And actually, the next thing I want to talk about is more on this topic. It's called Cob Webbing Technique. And so this is sort of a graphical way to understand how does the terms of the sequence that comes from iterating a function look like in the picture. Okay. But again, I can only say so much in one video, so I really encourage everybody to read chapter 10 on the section Iterating Functions, where there are much better pictures than what I can manage to draw. But let me just say last few words on this topic. So Cob Webbing. So what is Cob Webbing? Why is it called Cob Webbing? So I'm going to draw a picture. It's going to look like a cobweb. So, so basically, suppose we're interested in geometrically understanding the steps of the iteration, right? So we're interested in understanding geometrically the steps of the iteration. So I have my x0, which is my initial input. And I have my function f. This is my function to iterate. So again, iterate just means compose with itself many, many times. And I have my procedure to define my sequence. So x sub n plus 1 is obtained by applying the function f to the previous term. Now, so there's a technique that's called Cob Webbing that helps us visualize what's going on. So let me draw the graph. So there's my y-axis, my x-axis. So I'm going to draw the graph of f. I don't know what f is, but let's just say it's something like this. Okay, so maybe it's something like this. So this is graph of f of x. also, I'm going to draw in blue the line y equals to x. Okay, so this is the line y equals to x. So it's the graph of the function f of x equals to x. Okay, so we start somewhere, right? So let's say we start at x0. That's my initial point. Then to find x1, I have to look at the function value, because by definition, x1 is f of x0. So what I do is I just go up. So I just go up like this until I meet the function, graph of the function. So this y value, by definition, is x1, because it's equal to f of x0. Well, next, I need to find out where x2 is in x2 is, but that means I need to look at where x1 is here first. But the way I do that, I can just, oops, so x1 is actually here. So this is my x1, right? So because this is the line, this blue one, like this is the line y equals to x. Well, if x1, so if you want to find where x1 is on the x-axis, you can just follow the line from here to here. So now that's my new input. That's my new input. So now to find x2, I need to start from x1 and go up until I hit the graph the graph of the function. So the y coordinate here will be x2, because x2 is what happens when you apply function f to the input x1. Well, now that I have x2, I need to, that's my new input. So I need to figure out where x2 is on my x-axis. Well, I can go from here until I hit the blue line y equals to x. So then this one is my x2. And then I take this, the x2 is my new input. I found x3. I find x3 by just seeing where I meet the graph. And it's here. So x3 is here. And then again, I iterate by finding x3 in my x-axis, which means I go up until I hit the blue. That's my kind of x3. And then again, I go up until I hit the graph. It's x4. So here it would be x4. Okay, now it's kind of becoming impossible to read. But as you can see, it's kind of like, it looks like a cobweb. So I keep going until I hit the blue, then I go up until I hit the graph, and so on. I iterate. And so you can see in this picture, we're actually converging towards where the blue line meets the graph. And that should not be surprising, because where does the blue line y equals to x meet? Where does it meet the graph y equals to f of x? Well, to find the intersection points of two curves, you just set them equal to each other. And that's exactly f of x equals to x. That's exactly why you end up getting fixed points. Okay, so fixed points show up in this way because that's exactly when the blue line meets the graph. And it's clear that there's some sort of convergence happening here. These Cob Webbing procedure ends up converging to this point in this case. Okay, and so yeah, so that's it for today's lecture.